Welcome back, everyone. And off we go. Roadmap. Fall 19, Test 2, Part 2. Where do we even start? We start right here. We have an aldehyde with hydroxide in the first step, and then hydroxide and heat in the follow-up step. This is your big clues that you need an aldol reaction product here and an aldol condensation product here. And we'll start with those two things. Copy the molecule to predict aldol products. The alpha position will be making a new bond to a second version of the same molecule. This is a simple aldol because there's no other molecules listed. We make an OH in the first step. And we go 1, 2, 3, 4. Ethyl off the second last one. And then keep in mind what we just reviewed about steric hindrance. We'd want the bulkier group near the carbonyl. And we have our double bond, alpha beta. Put the carbon groups to the right near the carbonyl, not the bulkier ethyl butyl group. And that is an aldol condensation product. It's one of my favorite things in the world to follow that up with a 1,4 addition. And clearly we're seeing this blue piece is here. I'll circle it in blue. The green piece is here. I'll circle it in green. Let's see. Yeah. And the new piece is in orange. And it added 1,4. The new piece is exactly this species missing its alpha H. It's a suitable, let's see what we got here. We got a carbonyl here. It's a 1,4 nucleophile because it resonates both ways. It's the conjugate base of something with a pKa of 10. And that fits the bill there. And since we're on the subject, this molecule is going to react with hydroxide and heat. Remember what happened last time we did hydroxide and heat? We went from here all the way to here. It was an aldol condensation. In this sequence, we have the parts we need, nucleophile and electrophile in the same molecule. See the two carbonyls? I don't know if I'm going to be nice enough to give you those numbers. Those numbers are really nice. They're the only numbers that will give you a ring size 6 in the Robinson annulation. Robinson. And following those numbers, we'll go with all blue. And we'll have a 6 and a 5 and a 4 and a 3 and a 2 and a 1. And off of 1, there's nothing, but 2's a carbonyl. 3 has a formyl group. Yes, F-O-R-M-Y-L. Formyl. And 4 has a ethyl propyl group. 4 has an ethyl propyl group. We could follow the system up there, just draw the ethyls. I think it's easier to draw the ethyls. 5 has the same group. 6 got attacked and was temporarily looked like this. But with the heat, that gets lost and you get a double bond between the alpha and beta positions. So there we have a molecule that's set up for another 1,4 addition or 2. And what's going on there? Looks like things got, that guy is this guy. And it looks like it was flipped ever so slightly, doesn't it? Why don't I put the numbers here towards the formula? Ketones 2. Oh, pen's off. And 6 is attached. 6. Let's see. 2, 3. 3 doesn't have a group on it. I'm wondering. 3 has the formula. Oh my, oh my, oh my. 3 has the formula. See, I got rotated in my head too. 3 is connected to 2, which is a ketone. 1's there, 2's there. That's the piece that got added to 6. Sorry, I already had a 2. And 5 had the same group as 4. So that's the new group right there. Sometimes it's hard to see what's new and what's old. That's a 1,4 addition of this enolate. That's an N up there. And you need a proton source. After the 1,4 addition, you get an enolate intermediate, and alcohols are very common solvents for those. If you're doing a 1,4 addition, just go ahead and throw an alcohol solvent in there no matter what. You want to go ahead and do it again since we see the next one's a 1,4 addition as well. The new group is an organic group. You're saying, oh, I'm just going to use an organolithium, right? Organolithium, beautiful. No, organolithium is going to add 1, 2, probably to the aldehyde first if you want to make another argument. That's less hindered than this. Organolithiums do not know how to add 1,4. We got to we go through our brain processes. The list of nucleophiles for 1,4 addition. And we see one of the ones down there that's an organocopper chemical called a Gilman. So we need the benzyl Gilman. Phenyl CH2. Remember, Gilmans have 2 of those and a copper and a lithium. Benzyl right here. I know it's not that clean. I had to cut my page in half. And this bond is a lot cleaner than the original. There. And those are almost dead ends, but they're not. I want to go till we hit dead ends. They go forever. All right, what's going on from here to here? Oh my. There's a lot of good stuff going on there. That's why it's 3 points. It's a whole bunch of fun. If you look carefully, we decarboxylated eventually. And we made an imine using an NH2. Remember, you need an NH2 to make an imine that was attached to a CH2CH2. So if this could become an NH2 attached to a CH2, and after decarboxylation, that would be a CH2, that would provide the necessary functionality to make the imine. So one of the things we have to do is reduce the nitrile without reducing anything else. And a good way to do that would be H2 and PT. No pressure. No, seriously, don't add pressure. If you add pressure, your carbonyls will be gone too. 2 of them, the ketone and the aldehyde. It would not touch the ester regardless. So now you've got your CH2, NH2 up top, ready to make an imine. It might make an imine already. It's going to go imine with the aldehyde. That makes sense. It's easier to get to. It's less hindered. The ketone stayed the same on 2. I think that's going to do it, isn't it? Oh, we got to decarboxylate. Yes. What is the protocol for decarboxylating? And I hope somebody's going to ask me to do a decarboxylation saponification mechanism a little later. It's probably already waiting in my mailbox. I haven't gone that far yet. 2, you got to saponify the ester. This is the protocol to get rid of an ester that's beta to either a carbonyl or a C triple bond N. So alpha, beta, or the other way around. This carbon, there's an alpha to it, and the carboxylic acid is beta. But we don't have a carboxylic acid. We have a carboxylate after step 2. We have to protonate it to make a carboxylic acid. And when it's beta to either a carbonyl or a nitrile, all you have to do is heat it for the decarboxylation. And you are home free. Yep, there were 3 things in there. Want to get to one dead end at least, finally. H2 and PT is going to make that an NH and a CH, and it will not touch this. And what's going to happen after that is addition to the ketone with an ethyl. That's a nucleophile, and this is no longer an electrophile at all. And HCl will make an alcohol where we used to have the carbonyl. So I don't know. I'll draw it out. I was going to copy paste. That's not fair to you, though. And that goes to N with an H. Goes to CH. We got this funky ring in here. And I missed a carbon at the bottom. You get good at drawing hexagons in organic chemistry, that's for sure. Got carbon there. We got our favorite groups down here and here. And the carbonyl is now an OH. We have a new ethyl group on there. Nope, looks like a double bond with a nitrogen thing there. There's your ethyl group. And that is that. And finally a dead end. And what's going on here is, looks like everything got reacted with nitrogens, no more carbonyls. The secondary, the ketone, sorry, became an enamine. And so did the aldehyde. We needed a secondary amine for both, and they look like they're tied together with this propyl. So this is just good old diamine action. Ethyl on nitrogen with H. 1, 2, 3 carbons between with an ethyl and H and a geminal dimethyl on top. And you want to show off, you can even put DST in there, because both of those reactions are condensation reactions. And we don't have a dead end there, but we do have reduction of the double bonds and either allylic or benzylic bromination. That's when you see NBS, you should be thinking about that. After you reduce these pi bonds, there are no more allylic possibilities. So benzylic bromide is going to be here. And I don't even, well, there's no short form for drawing this thing out. You got your hexagon. You got your really tall hexagon with nitrogens in the middle. I don't even know if that was a good description. Didn't help you at all, I know. Ethyl on each nitrogen. And what else? Those double bonds are gone. We got our favorite group down here. Down here as well. 2 things here. Phenyl and our new bromine. And what's going to happen to our bromine? Lithium and hexane is going to make it into that's a terrible looking bromine. Lithium and hexane is going to make it into organolithium. And the next step is how we make a Gilman. There'll be a Gilman with two of these groups. It's a good thing we don't have to draw the Gilman. There'll be two of these attached to the copper, and that will add 1,4. 1,4 addition is huge on this test. You know that, right? It will add 1,4 to the back end of the beta position of this. So please, this is the time to circle in our group if there ever was one. Equals R. R is going to add a new bond to the beta position. There used to be a double bond here, and there is not. Used to be a double bond there. There's the double bond. It got attacked, resonated up to make an enolate, and as promised, 1,4 addition should always have some kind of alcohol solvent. Not always, but hey, for us, 1,4 addition should always have an alcohol solvent, and your life will go better. So we have a dead end there. And let's explore the top of the roadmap here. Since we're on the right here, LDA ethyl butanoate. Ethyl attached to butanoate. 1, 2, 3, 4. That's that one right there. And what it's going to do is react. It's LDA is going to make we're over here. Keep track of where we are. LDA knows how to take alpha H's. That's its job. That's going to be gone. Ethyl butanoate gets attacked and the leaving group gets booted off, and you deprotonate and get something like this. And then step 3 puts an H on there. So let's copy this piece here. Put it in blue. Got your new bond here to butanoate. As a group, it's called a butanoyl. Butan, OYL. And that's a dead end. I probably wanted to do things with it and didn't see a way because there's no room. What about going down here? How do we go back to an alcohol? It's not the alcohol. We didn't start with an alcohol. That's rare. Anyway, review aldehyde ketone reduction. You could use sodium borohydride followed by HCl. That's a good choice. Could use H2PT and pressure. Don't forget pressure or else you don't get a reaction. But I'm not going to write that there. This is on every test, of course. We're going to react it with PBr3. We're going to make an organolithium, and it's not going to add 1,4. That's the aldehyde of the same molecule down here, way back. Yeah, organolithium is going to add 1,2. So you're going to get a new bond to this carbon with this group. So the double bond hangs around. Double bond hangs around. Here it is. The aldehyde is now an OH. You've got a new bond. And we can go R prime. It added 1, 2. The H came from HCl. And my goodness, we have, I will not be doing this to you, I confess. But this is a review reaction of chiral epoxide formation. I think I went one step too far that semester. Why don't we make it more appropriate for what you might see on Wednesday? I'm not going to throw the sharpless asymmetric epoxidation at you on Wednesday. No, not during COVID. No, no, no. We can go with MMPP. Those are P's. And you should know that's going to make an epoxide. We love epoxides. They're very useful for synthesis. We have R prime in epoxide. So I would not be worried about stereochemistry anymore. So you could replace that with just a normal bond on your test on Wednesday. No wedge dash action. Just make it. Where's my eraser? I have not picked my eraser. Doesn't like me. I can't erase this because I grouped it with something. I'm sorry. What's going on here? Yeah, we got a lot of stuff going on. There's stuff going on. That's why the box is kind of big. I don't see my alcohol anymore. I see my R prime. The R prime is this here, just a reminder. Sometimes recircling is not a bad idea, just so you know where you're going. So R prime attached to a C with an O, C with an O. So that O is used to make an acetal. Ah, an acetal. We need another O, another alcohol. 2 alcohols are required to make an acetal. Oh, and here's my new bond. New bond in pink. How did that get there? On the less hindered carbon of the epoxide, that was acetylide, wasn't it? Acetylide. And step 2, protonate that O. So now you have a diol, this diol right here, OH and OH. And you don't have this group, and this group, how do we know this came from an aldehyde or a ketone? Well, it's a carbon with 2 bonds to O, and it's not present up here. And the carbon with 2 bonds to O was an aldehyde that had 2 bonds to O, and it had 3 carbons total. And HCl's H2SO4, sorry, is a catalyst that we use for that. And it's a condensation, so you can show off with some DST. There we go. And we have a lovely product. That's a gem. Back to the top. We're exhausting the right side. We got to get here from the left side. This is a fun roadmap. What's going on here to here? 2 things, apparently. This is the oxidation state of an aldehyde. This is 1 more bond to O. That's a carboxylic acid derivative. So if you're going to make it, a good way is from a carboxylic acid. How do you make an aldehyde into a carboxylic acid? You can use your favorite chromic acid oxidizing combination, H2SO4 and water. And then make your favorite esterification combination with ETOH. Fischer esterification gets the job done here. And sulfuric acid. And you can show off DST again, because it's a condensation reaction. Oh, we didn't finish with this one either, did we? Confused. I'm going to just run down the left side of this page. What's this thing going to do with LDA, propanal, and HCl? Well, an aldehyde will react with an enolate in an aldol reaction. Here's the H that has to go. LDA will take it. Have our 2 ethyl groups. Alpha position, CO2ET. This is a directed aldol condensation. Condensation. Sorry. Keep changing my mind. I saw the heat after the HCl. So I'm going to draw this OH. It's not going to last. This is after step 2, propanol, 3 carbons, 2, 3. That's step 2, finished. Well, O minus after step 2. In step 3, O minus becomes OH, but then with the heat, acid catalyzed dehydration also ensues. And we have a double bond with the carbon group pointing towards the carbonyl of the alkene. Ooh, the double bond's not there. Double bond's alpha to beta. Always don't be randomly putting double bonds in weird places. Has to be alpha beta. You take the second alpha H, and the OH that used to be here gets eliminated. And that is a dead end. Weird. This is not a dead end. What's going on here? Okay. Well, once again, this is a carboxylic acid derivative, and this is nowhere near the right oxidation state. To get to here, we need a carboxylic acid first. CrO3H2SO4AQ again. You're up to a carboxylic acid. And the only way we know how to convert a carboxylic acid to acid halide, SOCl2, and pyridine. PYR is not optional there. Looks optional in the corner there. There. Okay. You've made an acid halide. It's going to react with an amine and make what functional group? Aminolysis of the top 3 carboxylic acid derivatives always yields amide. Ethyl, carbonyl. New bond to an N that's got 2 ethyls. I was very ethyl happy on this, wasn't I? And then what's going on here? We have a 1, 2, 3, 4, 5 carbon piece with a carbonyl here and an amide, and now it needs to become an amine. This is the only reduction of an amide that we learned, and the only way we could do it was lithium aluminum hydride, which is always followed by some kind of acid, most commonly HCl. And you made an amine. Very nice. And now what's going on here? We have a carboxylate. That's a nucleophile. We have an acid halide with a leaving group. These things don't look the same, but they pretty much are. The one in right here, I'll draw in blue. Chlorine gets replaced by an oxygen that goes to a CH2, that goes to a, it goes to carbonyl, that goes to a CH2, that goes to a C with an ethyl and an ethyl. That is a symmetric amide. And then there's the leaving group. Look, this is the same as the thing here. And an amine will react with a carboxylic acid derivative of either the top most reactive variety or the second most reactive variety, anhydride, to make an amide. Keeping the blue piece going here. Black piece leaves. It's drawn above the arrow. And this is a primary amide. I always have nice things I can do with primary amides. What set of reagents will make this into the thing that has the same number of carbons? Let's verify. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same number of carbons, but the carbonyl is now a CH2. We did that right here. That's lithium aluminum hydride followed by HCl. Everything we've done is valid for your roadmap. There's just going to be less repetition. There's a lot of things that show up in here 3, 4 times, not even just 2. I'm going to cut that down to 1 or 2. That's how I make it half as big. Now this reduction is not really a reduction, it's a decarbonylation. And you lost this carbonyl, and that is the classic Hoffman rearrangement. Chemicals required for that are bromine, NaOH excess, and water, aqueous. And that gives this. If you're curious, the other product is carbonate, CO3 2-. And another dead end. This one's not a dead end though. We have an amine, and this thing, which is, I'm going to redraw it. We'll do it in black. Double bond to a C that's a carbonyl to a CH3, a acrolein. You don't have to know that name, but there it is. That is a nucleophile. The question on the table is it a 1,4 nucleophile? And the answer to that is yes. And the reason is it's the conjugate base of an ammonium ion with a pKa of 10. So amines add 1,4. And 1,4 addition, surprise, surprise, there's a solvent that's an alcohol in there. Lots of clues. So there's the part that got attacked. Here's the new bond to nitrogen, NH. It lost its proton to the alpha position. If you want to do, oh, you can get that from the nitrogen or from the ethanol. Probably the nitrogen's a better source. And don't we have an R prime that includes some stuff? CH2 twice, then the thing. I think that would be CH2 twice, then the thing, R prime. Well, it's right here too. Put it in red. And there's the R prime. This thing here went to a ketone right here. All the carbons here, 1, 2, 3, 4, are here. 1, 2, 3, 4, 5. Oops. That happens sometimes. I miscounted the carbons. It wasn't my intention. It's a dead end. I want to count again. 1, 2, 3, 4, 1, 2, 3 with a carbonyl CH3. That's correct. 1, 2, 3, 4, 5. 1, 2, 3, 4. It's just a mistake. My apologies. We'll fix it here. I want that, and I need my white out. Yeah, I know we need a break real soon. This will be a good spot for a break after this whiteout. There we go. And that's a bit of a big bond. We will finish this roadmap on the other side and move on during the next segment. So I'll see you very soon.